Okay, the next part of our homework starts with putting momentum into a system. So we have the overall momentum in the system is going to change. So this is really we add energy to the system, and that's where putting the energy, the momentum into the system is done when we add energy. So when you add kinetic energy, if you were going to try to just add momentum to a system, you can't without adding energy. So when you try to add momentum to a system, you are adding energy. Um, so there's no separate word for adding momentum to a system. The word work is a word that we use when we add energy to a system. And we're going to talk about what this system thing is a little bit down the road. But when we have kinetic energy going in our system, we have momentum because if there's a kinetic energy, there's a mass and there's a velocity. And momentum is all about mass and velocity. So you have both kinetic energy and momentum when something that has mass is moving. Now, when we say momentum is conserved, I should really say momentum is conserved in collisions. Momentum is conserved in elastic collisions. When we look at our pendulum, back up here, we saw that the kinetic energy is zero here, so there's zero velocity, and then it speeds up until the fastest point, and it's right here. In our Newton's cradle, that's the point where the pendulum bob is going to collide with the other pendulums in our Newton's cradle. In that collision, momentum is conserved. But overall in the system, the momentum is going to change based on how fast the thing is going. So we have to think about conservation of momentum in the system. Okay. Conservation of momentum during the collision. So momentum is conserved in elastic collisions. Okay, there's a funny aside here, so I'll cover this for those of you who aren't going to read. My husband and I are teaching our 15-year-old how to drive. When we talk to her about safety, we sometimes talk about how careful she needs to be around large trucks on the road. We tell her, remember, the biggest M times V always wins. This may work for warning her about big trucks because she will remember that their much bigger M will mean their momentum is higher in a crash. But we may have inadvertently been teaching her something very bad for driving. Can you spot it? So, can you spot how she could change her momentum even if she can't change her M, and how that might be a bad thing to teach our 15-year-old about driving? Okay, so what are we talking about with a system? So this is where we talk about a system. A system has a specific definition in physics. Work had a specific definition. Work is when I add energy to a system. A system has a very specific meaning, and it comes from this, it's particularly used in something we call thermodynamics, and that is a very fancy sounding word, and yes, you can now throw it around in conversation that you do thermodynamics. Thank you very much. It comes from, it's a little bit dated for a word for what it really means, because it came from when they were trying to understand what heat was. And so they were looking at heat, dynamics, how things move around. They were looking for how heat moved around. And one of the people who was looking at this was a very famous person in the beginning of chemistry. His name was Antoine Lavoisier. So his name is right here, Antoine Lavoisier. And he was fascinated by how mass and heat moved around in an experiment. And he would create these, he used his enormous wealth, he was a very wealthy person in France, and he used it to create these vessels that wouldn't explode when he was doing, or implode when he was doing experiments, so that he realized that the mass might move around, but it stayed the same. It might move from oxygen in the air to rust in a rusty nail, but the mass of the overall thing was going to stay the same. And he was also able to study how heat moved around in a system. And so the whole way of studying this, the conservation of energy and the conservation of matter, which was sometimes called Lavoisier's rule, was he would design a border around something, an experiment he was going to study, and then he would observe whether the heat or the energy flowed across it. Okay? And so the system was whatever experiment it was, and everything else is out of here. And so this dotted line is how he would set up the system. And then he would observe, is heat going across? Is matter coming in and out? Are other kinds of energy going in and out? And this is what we mean by the system. And this is a huge part of thermodynamics is knowing where to draw the system lines. This didn't work out really well for Lavoisier because he was also in charge of gathering taxes in Paris. And when he was gathering taxes in Paris, he thought, well, the problem was people were coming in and out of Paris and not paying the tax. And he said, oh, the best thing to do is draw a wall around your system of Paris. So they built this huge wall around Paris, and they only had a few gates that you could go through. This wall is still up in huge parts of old Paris today. And so they only had a few gates, and so they could track very easily who was coming in and who was going out, and they could tax them. Well, people didn't like the fact that they now had to pay their taxes. And so when the French Revolution came, unfortunately, this is thought to be one of the leading causes that he was executed during the French Revolution. So France lost a great scientist because he applied his thermodynamic principles to gathering taxes. So it's very sad. But it is good to remember when we're talking about thermodynamics that it's all about the wall. It's all about where we draw the wall. So for our experiments today, the wall is drawn around the system of our Newton's cradle. Okay, now let's watch some momentum being conserved during an interaction or a collision. And we're going to use the collision lab from Colorado, the FET.Colorado. Okay, so you can go here. Oh, I think it's right here. Oh yeah, okay, so it's right here anyway. Okay, so this is the collision lab. I showed a little bit of it during our class. The first thing I have in the homework packet is you set the red ball and the green ball are going to be exactly the same mass. Okay, and this is showing the velocity. When I press play, inside this system, this ball will have this velocity. I'm going to show the momentum instead, which is the mass times the velocity. It's measured in different units. Okay, and when we press start, there is 0.5 kilogram meters per second of momentum. That's how we measure momentum. So I'm going to slow the simulation down, and we're just going to press play until we have a collision. Then we're going to stop. Okay, notice that if I look at the overall momentum, it's still the same. It's transferred from one particle to another inside of our system. But in the collision inside of our system, the momentum is conserved. Okay, so that's it. That's the big lesson from there. Now, something interesting happens when I change this up. So let's restart it, and we'll make the second ball twice as big. Okay, the second ball is now twice as big. So let's see what happens. Now they're both moving, but this one's moving backwards, and this one is moving forwards, but its momentum is very different. So the momentum of the second one is 0.67 in this direction, and this one is negative 0.17, so it's going in the opposite direction. Notice if you add these two up, the momentum still totals to be the same. So before the collision and after the collision, the total momentum is the same. Okay, that is the big idea for that. All right, let's go to the next section. So see, we've covered a whole bunch. Oh, let's talk about set elasticity to 100%. Notice when I did this, elasticity is over at 100%. If it's squishy, so elastic means it's going to bounce back. It's not going to absorb any energy in its material. When you bounce a rubber ball, it deforms, and when it deforms, some of the energy of your bounce is lost to heat. So the ball will actually heat up. Different things happen within the ball, and that has to do with elasticity. So to get a perfect collision, we have to say it's 100% elastic, and there's no such thing as 100% elastic material in the world. it's quite, we need that for our simulated result. Okay. All right, after the balls collide, the same momentum. Okay, and then after the bigger one, it adds up to the same. Okay. Now we're going to go back to our vectors. We're going to look at our vector stuff from class. So in class, we talked about this vector simulation that you could play with here, and that we're using the Pythagorean theorem. We just are, what this says is any vector, well, this is called a vector, so this is it's just anything in our xy coordinate can be divided into an x part and a y part. We're going to need that in our next video when we see we're going to collide multiple particles, and we're going to see that overall they're going to go in a bunch of crazy directions, but overall if we add up the x and we add up the y, they will add up to be the same. They will add up so that momentum is conserved. So I'll show you that in the next video.